Part 3, the second derivative test. In this section, we're going to investigate the role the second derivative has in finding maximum and minimum values. To do this, we find the critical values of the following functions. Okay, identify the critical values as maximums or minimums using the first derivative test. Okay, so that's the number line and the regions of increase and decrease. Then we're going to take the second derivative and see how it can help. So first off, we're going to figure out the derivative of this guy. So that is 3x squared plus 12x plus 9. Okay, and we want that to equal 0 now. So 0 equals, now there is a common factor of 3, so we're going to take that out. Plus 4x plus 3. So that, of course, can factor, so 3 and 1 plus and plus. That is the world's worst 3. There we go. Okay, so x equals -3 or -1. Okay, so that's the number line for this guy. So -3, okay, -2, -1, and 0. So make the dotted lines for that. Okay, so now we can check some stuff. I checked out -4. I also checked -2. That's in the middle region. And I used 0 for the other one. So that's f prime of -4, -2, so and of 0. So we want the derivative of those. Now remember, the only important part here is the sign. So let's see, -4. -4 plus 3 is -1. -4 plus 1 is -3. So this guy worked out to be a positive. Right? Because they have a negative times a negative, which is also positive. So -2 plus 3 is +1. -2 plus 1 is -1. So a positive times a negative, so that guy is negative. And 0 worked out to a positive. So you have a positive region, a negative region, and then a positive region again. So what that means is that our -3 value, so from 4 to 2, okay, so that was going from an increase, so increasing, flat, and then decreasing. So -3 is a max. Okay, and that means that the -1 in between 2 and 0, so the -1 goes from decreasing, flat, and then increasing, so -1 is a min. Okay, well that's cool. All right, so looking at B. So y prime equals 4x cubed minus 12x squared. Okay, and then that's minus 16x. That's great. Set that equal to 0. And oh, look, this time we don't just have a common factor of 4. We have a common factor of 4x. So now we take that out and you get x squared. 12 divided by 4 is -3. X squared divided by x is 3x. And 16x divided by 4x, that worked out to -4. Okay. So 0 equals 4x. We factor this. And we get 4, 1, negative, and positive to make that work. Okay, so our critical values then are x equals 0, 4, or -1. So we set that up on the number line. Okay, so -1, 0, 1, 2, 3, 4. So those are our regions. Okay, and I picked for these -2 works. You can't pick -1 or 0 because those are both critical numbers. So we had to go -0.5 for that one. Okay, and then I picked point of 1 for this guy. And then I also picked 5 because he's the next number in the right region. So f prime of 5. Okay, when you figure those out, just type them into your calculator. Again, the only important thing is the sign. So that one was negative, this one was positive, this one was negative, and this guy was positive. So negative, positive, negative, positive. Okay, so that means the -1 goes from decreasing flat to increasing. So this guy is a minimum. Okay, so the -1 is a minimum. Okay, the 0 is increasing, flat, and then decreasing. So that is a maximum. And the 4, 0, okay, or the critical number, that's 4. Okay, 4 is, that is going from decreasing to flat to increasing, so that is a minimum. Okay, great. Now this last one, I feel a little guilty because we've already done this exact one, but we should do it again. So y prime is 3x squared. So the only 0, or the only critical value there is 0. 0, so x equals 0. Okay, so that's what happens on that number line, 0. Now if you remember, f prime of -1 and then f prime of +1. Okay, -1 squared times 3 is +3, which is positive, and 1 squared times 3 is still +1, so that's positive. So we had a region of increase followed by another region of increase, and that was that point of inflection thing. Okay, so this is a neither max or min. Zero is neither a max or min. Now, for the next part, we're going to use the second derivative and see if that can help us. So we're going to cheat a little bit because we've already taken the first derivative. So the second derivative for this, we just look up at the first derivative and take the derivative of that. So that's going to be 6x plus 12. Now we're going to evaluate the second derivative at those critical values. So y double prime at -3. Okay, so -3 times 6 is -18 plus 12 is -6. Okay, and then y double prime at -1, so -6 times, 6 times -1 is -6 plus 12, that is +6. Okay, so let's see, we've already decided that the -3, okay, when x was -3, we've already decided that that is a maximum. Okay, and when x was -1, that was a minimum. Okay, we've already decided that from above. Okay, we're going to hope to see some patterns here. So the second derivative of b is, okay, so go back up to there, so that is now 12x squared minus 24x minus 16. Now again, we could factor this, but we don't have to because we're just trying to figure out the second derivative at those critical values. So, and I'm going to choose to go in order, so I'm going to go -1, x double prime of 0, and then x double prime of 4. Okay, and you just type those into your calculator, and y double prime of -1 was 20, y double prime of 0 is -16, and y double prime of 4 works out to 80. Now let's see, we've already decided that the -1, okay, that was a minimum. The 0, when x was 0, was a max. Okay, and when x is 4, we've decided that is a minimum function again, or a minimum value. Okay, and then y double prime for this guy. So 3x squared, so that's just 6x. Great. And we evaluate, so y double prime is 6x, so y double prime at 0 is just 0. And this was neither max nor min. Not max or min. All right, so let's have a look at these numbers and see if we can figure out some patterns. Okay, so how can you determine if the function has a local max min using second derivatives? Okay, so second derivatives. So if we look at all the maximum points, so maximum, the second derivative was -6 there. It was -16 here. Okay, so it looks like if the second derivative is negative, we get a max. Now look at all the minimums. +6, +20, +80. Hey, if the second derivative is positive, it looks like we get a minimum. So if the second derivative is negative, there is a max. If the second derivative is positive, is a minimum. It's kind of cool. Okay, and then look at this last one. When it was 0, when the second derivative was 0, it was not a max or a min. So when the second derivative is 0, you get neither. Or min. Now that's called a point of inflection. Okay, we've seen these before, points of inflection. Okay. Closing in on it. Okay, so the second derivative test is, this is just a summary of what we just wrote down. Okay, if f prime of c equals 0, okay, so that's a critical number. Okay, so the first derivative is 0, and the second derivative of that is bigger than 0, okay, then that point, there's a local minimum. So if the second derivative is positive, we have a local minimum, and the second derivative is negative, then we get a maximum. So that's kind of cool. So use the first and second derivatives to sketch the graphs. Okay, this is our last one, nice and short. Okay, so we're going to take the first derivative of this, of course, so f of x, f prime of x, so 2x plus 2. Okay, we want the first derivative to equal 0, that's how we get our critical numbers, so -2 equals 2x, so then x equals -1. Okay, so that is our critical point, so we want to figure out whether that is, okay, so f double prime of x, so that is just, okay, 2x, so that's just 2. Oh, interesting. So if it's just 2, well, 2 is always positive. I guess we could, do that anyways. F double prime of -1. See how there's no x in that? So it's just 2, okay, which is positive, which means this point is a minimum. Interesting. So the second derivative was positive, therefore it's a minimum. Now the only thing else we have to do is we actually have to figure out the other coordinate. That's just the x coordinate. So I have to go right back to the original function and figure out what the y coordinate is when x is 1. Okay, well, that works out to, you just type it into your calculator and it works out to -4, right? -1 squared is +1, plus 2 times -1 is -2, so 1 minus 2 is -1, minus another 3 is -4. So the point here is -1, -4, and we've already said that that is a minimum. So -1, 2, 3, 4, okay, and this point is a minimum, so it kind of looks like this. Very rough sketch, but kind of like that. All right, so that's interesting. So second derivative is positive, we get a minimum. All right, let's look at B. So f prime of x is 3x squared minus 12. Okay, so we want that to be 0 to get our critical values. So 0 equals 3x squared minus 12. Whoops, sorry guys. So 12 equals 3x squared divided by 3 divided by 3. So 4 equals x squared. So square root, so x equals plus or minus 2. Okay, so I've got a couple of critical values here. So now we go f double prime of x. So we figure out the second derivative. So that is 6x. Oh, okay, so just 6x, that's all right. Now we figure out our second derivative at those critical values. So f double prime at negative 2 is negative 12. 6 times negative 2 is negative 12, which is negative, which means this is a maximum. Okay, f double prime of positive 2, 6 times 2 is positive 12, which equals positive, which means that point is at a minimum. Okay, so we need to figure out the y coordinates. So f of negative 2. F of negative 2 was 17. And f of positive 2, f of positive 2 is negative 15. So this point here, we get negative 2 and 17, and positive 2 and negative 15. The negative 2, that was a max. And the positive 2 was at a min. So negative 2, okay, so the horizontal are each worth 1, but the verticals are worth 2. Okay, so negative 2 and then 17. So 2, 4, 6, 8, 10. 2, 4, 6, so 17 is about there. In the middle there somewhere. Okay, so that's negative 2 is 17, and then 2, 15. Negative 15. So 2 is here, negative 2, 4, 6, 8, 10, 2, 4. So negative 15 is about there. Okay, so we've said that the 217 is a max. So it's kind of going to do this. So it's a max. This guy's a min. So it just comes up kind of like that, kind of like that. And there you have it. There is a reasonable sketch of this graph. Okay, last one. So we take the first derivative. Okay, so 1/3 times 3 is just x squared. Okay, and then 1/3 times negative 1/2 is just negative 1. So that's negative x to the 1 minus 6. Okay. Here, let's go in different order. It doesn't really matter. So f double prime, okay, is 2x minus 1. Okay, so the first derivative equals 0 when we factor this. So we get x, 3, 2, negative, positive. Okay, so then x equals 3 or negative 2. Okay, so those are the critical values. So then we go f double prime of negative 2. So negative 2 times negative 2 is negative 4, minus 1 is negative 5, which is negative, which means this guy is a max. Then f double prime of 3, 2 times 3 is 6, minus 1 is positive 5, which is positive, which means it's a minimum. Oh, okay. Now remember the last thing we have to do? We have to go back to the original function and figure out the coordinates of these points. So we have to go f of 3 and f of negative 2. That gives us our actual coordinates. Okay, so f of 3 was negative 25 halves, which is just negative 12.5. Okay, and negative 2 is 8.33. Or 8 1/3, or yeah. Okay, now we've already decided that the negative 3, the positive 3, that was a minimum, and the negative 2 That was a maximum. So we have -2 and 8.33, so -2 and 2, 4, 6, 8, and a little tiny bit. Okay, and then our next point, so that's -2, 8.33, and then this one was 3 and -12.5. So +3, 1, 2, 3, and 2, 4, 6, 8, 10, 12. Okay, and then 12.5 would be a little tiny bit past that. Okay, so about there. Okay, 2 and 8, that was a maximum. Okay, and the 3 and 12.5, that was a minimum. And it looks something like that. So, there's the third part. You're done. Section 1, graphical features. Please do the formative assessment and then the summative, and you are good to go. Call me if you need anything. Thanks.